So, the electron has got its own spin quantum number, that means it can recess on its own axis. So, that angular momentum is defined by Planck's constant multiplied by spin quantum number into spin quantum number plus 1 divided by 2 pi. So, the value of S is given 1/2 or -1/2 depending upon whether it is processing along the applied magnetic field or opposing the magnetic field. For each value of ml, there are 2 electrons, 2 differing in spin. So, therefore, what we can summarize is no 2 electrons within any atom can have the same 4 quantum numbers. This is known as Pauli exclusion principle. Each electron differs from every other electron in a given atom in its total energy. That means, either the principal quantum number or orbital moment quantum number or magnetic quantum number or spin quantum number, all the 4 cannot be the same. At least in one of them, the electron should differ in every atom. So, this gives rise to a plan where we can keep on filling the electrons in and build up the elements. For example, for K shell we have principal quantum number n would be 1 and L should be n minus 1, that is 0, and ML should have 2L plus 1, that corresponds to ML should be 0, and hence it is a single orbital. Only 2 electrons are permitted in this orbital with differing spins. One could be plus half, another could be minus half. The orbital is of S type, that means it is symmetrical around the nucleus. Similarly, for L shell we have 8 electrons. So, according to Pauli exclusion principle, for M, N, O shells we have 18, 32 and 50 electrons can be accommodated. According to the principle of maximum multiplicity, when an electron enters a level of fixed principal quantum number n and I, that is L, no, not I, L values, available orbitals are occupied singly until each orbital is occupied before any pairing occurs. This is important for us because among the pi orbitals we have 3 orbitals in the px, py and pz in 3 different directions. Even then, the electron should go to the one electron should go to px, one electron should go to py and another electron should go to pz, then only another 4th electron can enter the px. So, like that, this gives us a plan to fill the electrons and build up the atoms. So, the knowledge of the exact order in which atomic orbitals are occupied is based on the interpretation of atomic spectra in terms of how spectral lines result from permitted electronic transitions. Heavier atoms have complicated atomic spectral patterns and overlaps occurring in the similar systems. You can take a look at this. This is the s orbital, that is round spherical, and p orbital, there could be 3 p orbitals, one along px, one along py and one along pz, and then d orbital shapes are like this, where the electronic probability, the probability of electron being found around the nucleus in this region of space is maximum, and then f orbitals we have shapes something similar to this. So, this is px, py and pz orbital. Now, the energy level diagram also will tell us that first the 1s electron is the 1s orbital is filled, in which 2 electrons are permitted, and then the next electron will go to 2s and then 2p then 3s, 3p, and then finally, there will be, as the electrons keep on increasing in number, the orbital energy levels can get mixed up and the electronic structure becomes complicated. So, this gives rise to a filling order. We can imagine like this: first is 1s, and then 2s, and then 3s, 2p, and then 4s, 3p, 5s, 4p, 3d. Like that, we can have electrons filled for each element, where atomic number increases by 1 unit and the electrons also increase by 1 number. So, if you go around looking at it and then try to fit the electrons in different orbitals, we will have hydrogen with 1 electron, and then helium with 2 electrons, then lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine that go on adding 1 electron each, and one atomic number also keeps on increasing. If you arrange all this in a proper order as described by Professor Mendeleev, we have a periodic table, and this periodic table is a summation of all the elements that we know on the earth, and this is the best way of representation. For example, here you can see all these are basically non-reactive elements, where electrons like helium, neon, argon, krypton, xenon, radon, they are all called as noble gases. And then here is hydrogen, lithium, sodium, potassium, cesium, rubidium, francium, where 1 electron is there in the outermost orbital, that is s orbital, and then beryllium, magnesium, etc. These are all basically divalent metals. And then we have transition metals, in which the electrons get filled up in the inner orbital, d orbitals, and the zinc, cadmium and mercury are known as post transition metals. And then we have non-metals in this region, 3a, 4a, 5a, 6a and 7a groups. And here you can see lanthanides as well as actinides, and here also inner filling of the d and f orbitals takes place, f orbitals in lanthanides and actinides and d orbitals in the transition metals. And you can see the portion marked in the red corresponds to silicon, phosphorus, sulfur, selenium, arsenic, tellurium, germanium, a little bit of tin, etc. These are all called as semi metals or metalloids, and fluorine, chlorine, bromine, iodine, etc. are all called as halogens, which are nothing but basically gases, but they are all found in the environment as salts when combined with the metals represented in this area. So, here we stop for the atomic structure. What I want to tell you at this stage is that the elements found in this periodic table are all in the nature available to us, and these elements are used in different combinations in different substances, and they enter into the atmosphere, etc. And then we have the problem of determination of these elements in trace and ultra trace elements. So, with this structure in our mind, let us go and take a look at how electromagnetic radiation interacts with these metals. All the analytical methods available to us for the characterization and determination of the analyte can be broadly classified into spectrometric and non-spectrometric methods. This classification is not exactly based on scientific principles, but it emphasizes the importance of spectroscopic techniques compared to other forms of chemical analysis. In general, spectroscopy refers to the interaction of various types of electromagnetic radiation with matter, but can be logically extended to include acoustic waves, ion beams and electrons, etc. In one form or another, all these techniques measure the change of the in the intensity of the radiation or energy changes when the matter is exposed to electromagnetic radiation, including X-rays, gamma rays, ultraviolet, infrared, microwaves, etc. and radio waves, etc. So, let us look at the nature of the electromagnetic radiation. So, what is electromagnetic radiation? The characteristics of electromagnetic radiations are best described by a classical sinusoidal wave model. This model fails to account for the absorption and emission of the radiant energy. Phenomenon associated with such processes can be explained by considering the electromagnetic radiation as a continuous stream of discrete particles of energy called as photons. The wave particle duality of the electromagnetic radiation is basically complementary to each other and rationalized by wave mechanics. So, a plane polarized electromagnetic radiation of a particular frequency follows a sinusoidal oscillation along the direction in which the wave is propagating. So, if the wave is going like this, the wave will be going like this, and it has got an electronic component as well as a magnetic component. That is why it is called electromagnetic radiation. Such a plane polarized wave is represented mathematically. So, mathematically an electromagnetic wave can be described as a sine wave, something like this: A is equal to A0 into sin theta, where A is the amplitude at any point, A0 is the peak amplitude and theta is the continuous variable. Now, it can also be represented as A0 into sin omega t, where omega t is equal to theta and omega is the angular velocity in radians per unit time. A complete cycle occurs when Wt changes from 0 to 360 degrees. This is called one complete oscillation or one period. Hence, the time over which one complete oscillation occurs is given by T cycle is equal to omega divided by 2 pi, or mu frequency is equal to 1 over T, that is 2 pi by omega. Now, for any wave moving at a constant velocity, we can write V as a velocity is the function is a multiple of frequency and wavelength. Now, where V is the frequency in milliseconds, mu is in hertz, that is cycles per second, and lambda is in meters. The frequency mu is proportional to the energy of the photon given by E is equal to h mu, that is Planck's Planck's constant h defined as 6.62 into 10 raised to minus 27 ergs when E is expressed in ergs. And if you express it in joules, its value would be 6.63 into 10 raised to minus 34 joules. And sometimes it is convenient to use wave number denoted by mu bar to describe the radiation for example, in infrared spectrometry. Then the photon energy is expressed as E is equal to h c into mu bar, where c is the velocity of light. Now, we have talked of so many properties of electromagnetic radiation. Let us take a look at the units, because these are the units we will be talking quite frequently. Now, you can have here it is nanometer, its a symbol is Nm, and unit is for wavelength, and this symbol nanometer or nanometer is used in ultraviolet, visible and near infrared regions. And you can also use angstroms and signal is like this, symbol is like A0, and X-ray, it is used in X-ray UV visible spectrophotometry in older work. You can also describe the same thing as millimicrons, and this is used in visible range, that is in older work. Nowadays, most of these units are used as nanometers, and wave number, as I told you, the unit is in centimeters inverse, and frequency divided by velocity of light. It is used in infrared as well as UV visible, but it is very less common, it is very less common in UV visible. You can also use electronic volts, EV, and unit for energy used in X-ray and gamma ray, and hertz is of course is a unit for frequency, and it is used in radio frequency and microwave application. Cycles per second is also is the unit for frequency, and it is used in radio frequency, but nowadays it is used very less in current literature. And the same thing I can tell you that it may be noted that regardless of the time of the units of expression, any electromagnetic radiation of frequency mu will have unique wavelength and energy. The longer the wavelength, lower is its energy and frequency. Energy is closely related to the temperature of any object also. It can be expressed as E is equal to, E is not equal to, E is proportional to Kb into T, where Kb is the Boltzmann constant and its value is 1.380 ergs into 1.380 into 10 raised to minus 16 ergs, and units are K inverse atom inverse, or 1.380 into 10 raised to minus 3 joules K inverse and atom inverse. If we consider energy per mole of the material, then E can be defined as being proportional to RT, where R is the gas constant and its value is 8.3145 into 10 raised to 7 ergs K inverse mole inverse, or 8.3145 joules K inverse mole inverse. Now, the energy of the photons should not be confused with the brightness or intensity of the source, but it relates to the color of the light. The power of a light source is given by P is equal to number of photons that it emits multiplied by the energy of the photon. It is the energy of a beam of radiation that reaches a given area per second. Intensity of a source of radiation is the power emanating per unit solid angle. This is a very important concept that we will be talking about later. Now, you can see the electromagnetic spectrum as consisting of a range of radiations. You can define it in terms of frequency, that is here. You can define it in terms of angstroms, micrometers, and then millimeters, centimeters and meters, etc. And you can define them in terms of specific radiation such as gamma rays, X-rays, ultraviolet, visible light, near infrared, far infrared, then we have microwaves, and then we have radio waves. You can see that the visible light is only a very small portion of the whole electromagnetic range, and this is composed of 7 colors, that is violet, indigo, blue, green, yellow, orange and red. If you take a look at this electromagnetic radiation, you can see that the range starts from 10 raised to minus 6 nanometers up to 100 millimeters, 100 megameters, that is kilometers, and the lowest would be gamma rays, and their range is from up to 1 angstrom units. All the radiation corresponding to this are called as gamma rays, and these rays can be used for the determination of elements for in techniques such as Mossbauer, etc. And then X-rays, they are, you know that there are different kinds of X-rays, soft X-rays and hard X-rays. Soft X-rays are used in medical science for the imaging the bones and tissues, etc., and hard X-rays are used for the determination of metals. And after the X-rays come ultraviolet rays. In the ultraviolet rays, we have far ultraviolet, then ultraviolet, and then visible region, vacuum ultraviolet. These are the three parts, regions of ultraviolet. One is vacuum ultraviolet, another is far ultraviolet, then we have normal ultraviolet. Up to 165 nanometers we have vacuum ultraviolet, and then between 165 to 180 it is all far ultraviolet, and 180 to 350 nanometers we have ultraviolet. From 350 to 800 nanometers we have visible range, and that visible range is represented by these areas, different colors. And then after that we have near infrared followed by infrared, and then microwaves, far infrared, and then followed by microwave and radio waves. You can see that all these ranges of the electromagnetic radiations are used in one form or the other of a spectroscopic determination. So, it is very important for us to know electromagnetic radiations. They are all used for the determination of several metals and then organic substances, etc., and all these things are used for the UV, visible, infrared, vacuum ultraviolet, and then we have infrared, far infrared, microwave, ESR, all the such techniques, they are all useful. Now, we would like to know how the radiation is transmitted, because whenever we use electromagnetic radiations in our instruments, there are two types of interactions will occur. One is regarding the interaction of matter with the instrument components, and another is interaction of the electromagnetic radiation with the sample. Now, this is how the transmission of radiation takes place. Before that, let us understand that the rate of propagation of electromagnetic radiation through a transparent material such as atoms, ions, molecules and particles is less than that of vacuum. However, frequency change will not be observed in the vacuum or elsewhere, which means that permanent energy transfer to the medium does not occur. Therefore, the interaction involved must be only temporary deformation of the electronic clouds associated with the atoms and molecules of the order of let us say about 10 raised to minus 14 to minus 15 seconds. Since the velocity of radiation in the media is wavelength dependent, the refractive index of the media also must change. the variation of refractive index with wavelength is called dispersion. So, essentially what we are talking about is interaction of electromagnetic radiation with materials, not the samples or analyte what we call it. Variation of refractive index is called dispersion. And what is this dispersion? Dispersion is basically a very complex phenomena. Dispersion curves usually show two regions. One is normal dispersion, in which there is a gradual increase in the refractive index with increasing frequency. Sometimes anomalous dispersion occurs at frequencies in which sharp changes occur coinciding with the natural harmonic frequency of some part of the molecule or a group of a molecule or a functional group of a molecule or of that of ion, leading to an absorption of the beam. So, in general there are two types of dispersions. One is normal, which shows the increase in refractive index with increasing frequency. Another is sharp changes occur. In spectroscopy, dispersion curves are important for optical components such as lenses. So, here the most suitable components for the manufacture of lenses are those in which refractive index should be very high and it should be constant. It should not show anomalous dispersion of the electromagnetic radiation. Now, why? If it does not show all these things, this results in reduced chromatic aberrations. For the fabrication of prisms, for example, you have to pass the radiation through a prism, and it should not show any other aberrations except changes in the frequency or changes in the wavelength. So, for the fabrication of prisms, refractive index should be as large as possible, but also highly frequency dependent. Similarly, diffraction. Diffraction refers to the bending of a parallel beam of electromagnetic radiation as it passes through a sharp barrier or a narrow opening. It is a consequence of interference which can be easily demonstrated in the laboratory. When a parallel beam of light is allowed to pass through a pinhole, two closely spaced pinholes are seen on a screen placed across it. If the radiation is monochromatic, what you would see is a series of dark and light images appearing perpendicular to the plane of radiation, like this. So, here we have a radiation going along and we have a small pinhole, and the radiation that are coming out on this side, where we place a screen on this side, you would see a sharp image of black and white, black and white, black and white. So, this phenomenon is refraction. Now, let us take a look at another phenomenon, that is reflection of radiation. So, what is reflection of radiation? Mirrors, you would have seen the objects in the mirror, and mirrors basically reflect the radiation falling on them without any loss of the incident radiant power. Hence, they are used for as optical components of a spectrum. Concave mirrors you would have seen in your cars and scooters and motorcycles, etc. They reflect the radiation as well as they concentrate the reflected radiation at its focal point. When radiation crosses an interface between media differing in refractive index, reflection always occurs. Some amount of reflection. For a beam entering an interface at right angles, the fraction reflected is given by IR upon I0, that is the refraction ratio, as N2 minus N1 whole square divided by N2 plus N1 whole square, where we can define I0 as the intensity of the incident beam and IR is the intensity of the reflected beam, and N1 and N2 are the refractive indexes of the two media. So, this is a very simple phenomenon. Some amount, no matter what you do, reflection always occurs, and reflection is not good in spectrophotometry or any other instruments unless the aim is to concentrate the reflected light, such as a concave mirror or something like that. And then what is refraction? Here I am showing you the figure of refraction. There is a light ray coming from one media, entering another media such as glass and going out of the glass again. Now, you can see that the light ray, even though it is parallel, even though it is a single beam, it does not proceed along the same way. Instead, it bends and then proceeds in another direction. So, you can see that there are two interfaces. One is this area where it is air or vacuum, another area is this glass or quartz or water or any other air medium in which light passes through, and from the medium again it enters into another medium. So, there are two interfaces, air, vacuum or air. Usually vacuum we do not come across in our day to day life where light passes through the vacuum. So, it is in general changed to air. So, you can use a vacuum also, but there is no problem, but the normal situations where we see are light rays entering from air into one medium and then passing out through the again into the air medium after the medium ends. So, we have a light ray that bends like this and then goes out, and this is perpendicular. So, when the radiation passes at an angle through the interface between two media having different densities, an abrupt change in the direction occurs here, abrupt change. This is called as refraction owing to the changes in the velocity of the radiation in the two media. So, the velocity of the radiation changes in the media. The extent of refraction is given by Snell's law, that is sin theta 1 divided by sin theta 2 is equal to n 2 by n 1, that is also the ratio of the velocity of the substances, velocity of the radiation in the two medium, that is V 2 by V 1. Now, all these things are college physics and chemistry. So, I am not going into details of all these things, but you can look up the college physics textbooks which will explain these phenomenon in more detail. For example, in vacuum velocity V 1 is equal to 0 and n 1 is unity. So, you can write n 2 is equal to sin theta 1 divided by sin theta 2. So, refractive indices of materials can be measured, and with air as one medium and available in databases, lot of substances which are capable of refracting a radiation falling on them are known, and these are available in the databases. Now, let us take a look at another phenomena, that is scattering of radiation. Momentary absorption of radiant energy by atoms, molecules or ions, followed by re-emission of the radiation in all directions is known as scattering. Particles having comparable dimensions to that of incident radiation removes most of the re-emitted radiation by destructive interference, except those travelling in the original direction, that is along the after passing through the substance. A very small radiation, particles having comparable dimensions to that of the incident radiation removes most of the re-emitted radiation by destructive interference, except those travelling in the original direction. A very small fraction of the radiation is transmitted at all angles from the original path, and its intensity increases with the particle size. This is one phenomenon. Another phenomena is scattering by molecules or aggregates having smaller dimensions than the incident radiation is known as Rayleigh scattering. Larger molecules, what do? they scatter the radiations in different quantities in different directions. This is called as Mie scattering. When the scattered radiation is quantized like those occurring in vibrational energy level transitions in molecules as a consequence of polarization process, then it is known as Raman scattering. This is another type of scattering which is quantized and used in the Raman spectra. So, what is polarization? Now, this is another phenomenon that is important for us to know what is polarization. Basically, what you see when a light beam is passing around, you would see that the electronic vectors are there, magnetic vectors are there, a beam of light passing through the through a media. If you view it from the receiver's end, that is, if the light is coming towards the observer, you would see a number of beams, number of parts, that is electrical and magnetic parts bundled together in a not so systematic manner, but it is a big bundle coming towards you, in which the electronic and magnetic vectors are mixed up in a big bundle without any sense of direction or something. Of course, there is a sense of direction, but you would see that they are not properly organized. So, if you put a vertical polarizer in a vertical plane, what you would see is all other things are eliminated except a vertically polarized light wave. You would see like this. This is known as polarization. So, ordinary radiation consists of a bundle of electromagnetic waves in which vibrations are equally distributed among a huge number of planes centered along the light path of the beam. Viewed end on, it looks like an infinite set of electric vectors fluctuating from 0 to a maximum amplitude A. The vector in any one plane, say xy, can be resolved into two mutually perpendicular components that we have already seen when we started studying the electromagnetic radiation. So, removal of one or of the two resolved planes of vibration produces a plane polarized beam. It occupies a single plane, and radio waves emanating from antennas and microwaves produced by klystron tube are plane polarized. These are the day to day experiences. You would have heard lot of radio, FM radio and other things, and microwave, you must be having a microwave oven also in your house, and the radio waves and microwaves are plane polarized in our day to day life. So, a polarized ultraviolet and visible radiation is also required. It is produced by passing the electromagnetic beam through a media that selectively absorbs or reflects or refracts that vibrates in only one plane. So, electromagnetic radiations we need which are plane polarized. Okay. So, let us look at the another phenomenon, that is diffraction of radiation. So, what is diffraction? Basically, diffraction refers to the bending of a parallel beam of electromagnetic radiation as it passes through a sharp barrier or a narrow opening. It is a consequence of interference which can be easily demonstrated in the laboratory. You also would have experienced the diffraction in your day to day life. For example, if there is a source of light that is passing through and a small opening is made, you would see interference fringes with light and dark, light and dark, light and dark patches that are visible here. Even in day to day life, such systems are very readily available if you have the patience to look at them around you. For example, when a parallel beam of light is allowed to pass through a small pinhole, two closely spaced pinholes are seen on a screen placed across it. Now, if the radiation is monochromatic, a series of dark and light images appear perpendicular to the plane of radiation. This is the one what I had showed you. In the above figure, it can be shown that Cf is equal to Bc into sin theta. For two beams to be in phase at D, it is necessary that Cf should correspond to the wavelength of the radiation. Therefore, lambda is equal to Cf into that should be equal to Bc sin theta, where Bc is the vector. Since reinforcement can also occur at 2 lambda, 3 lambda, etc., n lambda should be a function of the vector Bc multiplied by sin theta, where n is an integer called as the order of interference. Now, this diffraction, when the phase differences remain entirely constant with time and the system is said to be coherent. Then only a regular diffraction pattern is observed. The spacing of the bands depends upon the distance between the slits D, and the following relation holds good: n lambda is equal to d sin theta. This is a very famous equation, and you should not be forgetting in your entire career if you are undergoing this course. Now, if two different wavelengths of red and blue are used, the two colors will be separated on the screen. I will show you straight away, like no, it is not here. The two colors will be separated on the screen. If white light is used, a number of small rainbows containing all the colors will appear. By placing a moving slit across the screen, any color or wavelength can be selected. This principle is used in gratings. We will study more about gratings and their uses in spectrophotometry, which is very common nowadays, in more detail when we are studying the spectrophotometry and UV visible, ultraviolet, and then in atomic absorption, etc. Now, prisms are the poor cousins of diffraction units. For example, basically what is a prism? All of you would have seen prism. A prism basically disperses the incident radiation depending on its refractive index and its variation with wavelength. A prism can be used to disperse ultraviolet, visible and infrared radiation. The material of construction of course depends upon the wavelength region. For example, for ultraviolet, what you would need is a prism made of silica or quartz. For glass, ordinary for visible region, glass will do. For UV, for infrared region, you need salts, for example, sodium chloride, potassium chloride, potassium bromide, like that, salts which can be crystallized into this kind of prisms, which will disperse the infrared radiation. Here in this figure, you would see that when we are passing the white light through the prism, it separates into its components, starting from red, orange, yellow, green, blue, indigo and violet. These are the rainbow colors what you see normally in rainbows. Now, the same thing essentially happens here and in the nature also, where the raindrops act as the prisms for the falling when the sunlight passes through the raindrops and they get reflected at a particular angle, and you would see the rainbow colors into the sky, which is a beautiful sight to behold. Now, the same principle is used in these things in spectrophotometry as well as in atomic absorption, infrared, etc. And you can see that I have shown you two prisms here. One is 60-degree prism, that is this angle is 60 degrees, and they can be made from by the fusion. If you suppose you draw a line here, if you draw a line here, they are made by the fusion of the right handed and left handed prisms, one here and one here, right handed and left handed prisms, and by fusing together we can make a 60° prism. And the other one what I have shown what I have shown here is a 30° prism, and this prism is made by on one side it is coated with a mirror surface. So, the radiation here, the wavelength, the light of the desired wavelength comes through like this and then passes through and then goes out of the prism on the opposite direction. Now, here what is happening? The light is coming inside and then changing, going and hitting the mirrored surface, gets reflected and comes back on the other side. So, this type is known as Cornu mounting, and the 30° prism is known as litro mounting. A prism, this is called a cornu, and mirror black, etc. This I have already referred to you. Here the refraction takes place twice on the same side with less material coupled with the saving of space.